All right, so we're going to kick things off by looking at the in-class assignment from our last class meeting that we didn't have time to go over to talk too damn much. So for this particular in-class assignment, we are given a toroidal coil, which is something that we've looked at before. In fact, we derived things related to toroidal coils in our last class meeting. And we're told that the toroidal coil has an interior radius of 6 centimeters and an exterior radius of 7 centimeters. It is 1 centimeter thick, so that means we have a rectangular cross section. The coil that is wound around the toroid has 250 turns, and it produces a flux of 10 microwebers in the core. If the magnetic field intensity in the core is 1,000 amps per meter, we are asked to determine the length of the average flux path, the magnetic flux density in the core, the required MMF needed to sustain that 10 microwebers of flux, and finally, the amount of current that is flowing in the coil. I'm taking the time to go through this because we're going to use a lot of these relationships today when we get to more odd geometries and all of that kind of jazz. So let's first talk about how we are going to determine our the length of our average flux path. Okay. So the average flux path for this particular geometry, and really any geometry that we're going to deal with, is, as the name implies, the average distance that our magnetic flux travels around our magnetic circuit. So it's not going to be the interior radius or the length of the interior radius, nor is it going to be the length of the exterior radius. It's going to be the average value. So for us, that's going to look like the quantity R1 plus R2 divided by 2 is the average radius, right? So for us, that's going to look like 6 centimeters plus 7 centimeters over 2 is 6.5 centimeters, right? So that's halfway inside of our toroidal coil. Okay. So now I need to determine the length of my average flux path. Well, we can see from our picture here that our flux path is circular. So how do I find the perimeter of a circle with a radius of 6.5 centimeters? 2 pi times the radius, absolutely, right? So our average flux path length, L average, is going to be 2 pi times R average, or 2 pi times 6.5 centimeters. And if we throw this into our calculators, 2 pi times 6.5 gives us 40.8407, or 40.841 centimeters, which agrees with the answer that I provided. Okay. So part A, fairly straightforward. Now we need to figure out part B, right? So part B, we are asked to find the, let's see, magnetic flux density in the core, okay? So our magnetic flux density, by definition, B, is going to be simply our magnetic flux, phi B, divided by A, the cross-sectional area of our core. Phi B was given to us, right? We were told that it was 10 microwebers, if memory is serving me correctly. So how are we going to figure out our cross-sectional area? So our cross-sectional area, I even included a little picture here, is just going to be this distance, which is R2 minus R1, times the thickness of our core, which we were told was 1 centimeter, if I'm not mistaken. So this is our thickness of 1 centimeter. Let me scroll up and make sure I'm not screwing that up. Nope, that was what our thickness is. So our area is simply 1 centimeter. Let me write this out further. So phi b over R2 minus R1 times T. So that's going to look like 10 microwebers divided by 1 centimeter, which is R2 minus R1. And then our thickness is also 1 centimeter. So this is going to look like 10 microwebers per centimeter squared. Now, we were provided an answer that's in Tesla, which is the conventional unit for magnetic flux density. So go back in your notes and tell me what a Tesla is. Is it a Weber per meter squared? Is it a Weber per millimeter squared? Weber per meter squared. Okay. So right now we have microwebers per centimeter squared. So we're going to have to play around with some unit conversions in order to make this thing come out in something that's useful for us, right? So 10 microwebers per centimeter squared. So the first thing I'm going to do is I'm going to multiply by a factor of, let's see, so they're going to be 1 microweber is 10 to the minus 6 webers. And so this is going to give me webers in the numerator, which is what I'm looking for. Then I'm going to put 1 centimeter up here is 10 to the minus 2. Hold on just a second. 10 to the minus 2 meters, right? Because there are 100 centimeters per meter. I'm just doing the thing in the other direction. And I'm going to square that conversion factor to make the units work out correctly. Okay. So when I plug this into my calculator, I'm going to have 10 times 10 to the minus 6. So that's going to look like 10 to the minus 5 Webers divided by 10 to the minus 4 meters squared, right? Because 10 to the minus 2 times 10 to the minus 2 is 10 to the minus 4. And 10 to the minus 5 divided by 10 to the minus 4 is just 0.1. So I have 0.1 Webers per meter squared. And we know that a Weber per meter squared is simply a Tesla. So the units here can get kind of tricky. I'm trying to show you guys how to properly use our conversion factors and all of that kind of good stuff. So there's part B. For part C, we are asked to determine the required magnetomotive force, or MMF, needed to sustain our flux, right? So our magnetomotive force is N times I, the number of turns times the current flowing into a turn. We definitely have N, but we don't yet have I. In fact, finding I is actually part D of this problem. But we know that our magnetomotive force should be equal to our magnetic field intensity H multiplied by the length of our average flux path, right? So effectively, this is Ampere's circuital law, where the integral of H dot dl is equal to I enclosed, right? Where I enclosed is effectively our magnetomotive force, just N times I. So we have H. It was given to us as 1,000 amps per meter, if I'm not mistaken. And we have our average flux path of 40.841 centimeters. And we're going to need to convert centimeters into meters. So for every 1 meter, we have 100 centimeters. And if we look at what's going on with the units here, so this centimeters in the numerator cancels this centimeters in the denominator. And then we are going to have this meters here in the numerator cancel this meters here in the denominator. We're going to be left with amps. Realistically, this is going to be measured in amp turns, but a turn is a dimensionless quantity that's just counting the number of turns that we have in our system. Okay. So throwing this into our calculator, we have 1,000 times 40.841 divided by 100 gives me 408. Go away menu thing. 0.41, which that's from rounding. Amp turns. And then lastly, for part D, we're asked to find the amount of current required to sustain our flux of interest. And so I is just going to be our magnetomotive force, Ni, divided by our number of turns. So 408.41 amp turns divided by 250 turns gives us 1.6336 or 1.634 amps. So that's the current carried in our coil in order to sustain that flux of 10 microwebers. Why that accidentally zoomed out on me. All right, so we've got in-class assignment 1 knocked out. Now let's get to today's lecture where yes, Bailey. Where did I get the formula for part C? So, all right, so we know that the integral around our closed path is equal to J dot dA like this, right? Where this is a line integral and this is a surface integral, right? That's one of the first things that we learn. That's Ampere's circuital law. Okay. J dot dA, or the integral of J dot dA, is just the total current enclosed by our contour, which is going to be for a solenoidal, excuse me, for a toroidal coil like this, right? So let me draw this in purple here. So this line right here that I'm putting in purple is our contour of choice. Right. It's somewhere in the middle of our core, and it encloses a whole lot of turns of our wire. So the total amount of current enclosed by this contour is just N, our number of turns, times I, the current being carried by each turn, right? So we have Ni is equal to this business over here on the left. Well, the integral of H dotted into DL is just going to be H times L. because our magnetic field intensity is in the same direction as our contour, right? So our magnetic field intensity, our H field, is circulating around inside of our toroid, and our contour is also circulating around inside of our contour. So this H dot dl literally just looks like H times L. So this is equal to this, and it's dependent upon the geometry of the system. So generically, for this toroidal coil, this will always be true. Okay. So two is L. Yep. All right. So we are going to talk now about magnetic circuits. And we are going to use the results of our toroidal coil analysis. So literally, as we just discussed, magnetomotive force, MMF, is equal to N times I, and it is also equal to H times L, where L is our average flux path, right? So we have two different ways to represent our magnetomotive force, MMF. From our last class meeting, we derived effectively an Ohm's law-like relationship that said our magnetic flux phi B is going to be equal to our MMF Ni divided by fancy R, which is the reluctance of our core. And we defined the reluctance of our core to be equal to L, the average flux path, divided by A, the cross-sectional area of our core, multiplied by mu, the permeability of our core. So we are going to use these relationships to develop an equivalent magnetic circuit, which does not require complex calculus for us to solve. Okay. So let me ask you guys a question. Do you want me to work an example where everything is a variable, or do you want me to put numbers in it? Numbers, okay. All right. So I'm going to draw a structure here. I think I used blue for our core earlier, so that's what I'm going to use here as well. So this is our core. It is a three-dimensional structure. Like so, right? So I'm just going to put here core. And I'm going to wrap a wire around one of the legs of our core. We're going to say that this winding has n number of turns, where n is equal to 500. Our current is flowing in this particular direction. And our current I is what we're actually going to be solving for here. Now I need to give you the dimensions of our core. So let's call this dimension width 1. And it is 1 centimeter. let's call this dimension width 2, and it is 0.8 centimeters. And let's call this dimension our thickness, t, where t is equal to 1 centimeter. And then this distance from here to here will be L. And this distance from here to here will be the same, and it's also L. And let's say that L is equal to 10 centimeters. So our goal in this case is to, like I said, determine the current I that is needed to sustain a flux of phi b is equal to 0.1 Webers if our core has a permeability of 25,000 U0. So we're going to use this example to kind of illustrate the concept of an equivalent magnetic circuit for this thing. All right. So if we look at this relationship up here, we can rearrange things slightly to find that our MMF and I is going to be equal to phi b times R. And then we can take this one step further and see that I is then phi b times our reluctance R, let's call this REQ, go away, menu, REQ divided by our total number of terms. Right, everybody okay with this amount of algebra? So which of these numbers do we already know? Let's start there. We know phi b, and we know n. So the only thing we don't know in order to solve for our current I is the equivalent reluctance of this particular core structure, okay? So I'm going to represent this structure like an electrical circuit. So this is going to be the reluctance of the left-hand leg. Then I'm going to have a voltage source representing my MMF. Over here, I'm going to have the reluctance of that top leg. Over here, I have the reluctance of the right leg. And down here at the bottom, I have the reluctance of the bottom leg. So we know that reluctance in general is equal to length average. So our average flux path length divided by cross-sectional area times mu, right? So now we're going to have to use this relationship to figure out what the reluctance of each of these four legs in our magnetic circuit is. So let's deal with the leftmost leg first. Okay. So what is the average distance that our flux travels when it goes through the left leg. Okay. I'm going to draw this in purple. Okay. So this is what that length is going to look like, right? It's not going to go all the way from the very bottom up to the very top. It's going to start effectively halfway through the middle and then go up to halfway through the middle of that top branch, right? Because we're dealing with an average value here. So how would I express this total length? L minus W1. Absolutely right. Okay. What's my cross-sectional area going to be? So let me put this in red so that we can try to see things here. So our cross-sectional area, I'm sorry this graph is already getting so busy, is representing this area that I've outlined here in red. So what would that area be equal to? T times W2. And then I have simply my permeability, which is going to be the mu that was given to us, where we need to know the value of mu naught in order to calculate this, right? 4 pi times 10 to the minus 9 henries per centimeter is what we're going to wind up using. Okay. So let's throw numbers into this thing. Right? So W2 was 0.8 centimeters. T was 1 centimeter. And then we're going to have mu, so 25,000 times 4 pi times 10 to the, minus 9, not minus 19. Henries per centimeter. That's my denominator. And then I'm up on top, I'm going to have L, which was 10 centimeters, minus W1, which was 1 centimeter. So let's look at the units here and figure out exactly what's going on, right? So hopefully pretty obviously in the numerator, we have units of centimeters, right? Because centimeters minus centimeters is just centimeters. In the denominator, we have centimeters squared times henries per centimeter, which is going to look like henries times centimeters, right? So we have centimeters over henries times centimeters. So it's going to look like 1 over a henry. Well, a henry, if you recall, is a volt second per ampere, right? So let me write that down because it may have been a minute since you learned that. 1 henry is equal to 1 volt second per ampere, and we call volt seconds in magnetic circuits Webers, right? So this is going to be the same as 1 Weber per ampere, and we're going to call these amp turns because we're dealing with magnetic circuits. And so from this, we're going to find that our reluctance for this particular leg is 35.810 times 10 to the 3 amp turns per Weber, using the units conventionally associated with reluctance. Yes, Avery. Because mu is equal to 25,000 mu naught. And mu naught is 4 pi times 10 to the 9. So this guy right here is just the mu naught. All right, so I walked you through that calculation. Let me ask you guys a question. What should the reluctance of the right hand leg be? The exact same thing, because it has the exact same geometric structure, right? So R right is going to be the exact same thing as R left, 35.810 times 10 to the 3 amp turns per Weber. So now we just need to figure out the top and bottom, and hopefully pretty obviously those are going to have the exact same reluctance as well, because those structures are identical to each other. Right. So for the top, we're going to be looking at this length. Right. So how would we quantify that length I've drawn over the top part of our flux path? L minus W2. Absolutely right. So R top, which will be the same as R bottom, is going to be L minus W2 divided by, so what's our cross-sectional area up top? W1 times T. And then we need to multiply by mu. Right? So throw numbers into this guy. Let's see, W1 was 1 centimeter, T is 1 centimeter, 25,000 times 4 pi times 10 to the minus 9 henries per centimeter. Up here in the numerator, we're going to have 10 centimeters minus 0.8 centimeters. And so this is going to come out to be 29.285 times 10 to the 3 amp turns per Weber. And so what would our equivalent reluctance of the entire system look like? All of them added together in series. So twice R left plus twice R top, or R left plus R top plus R right plus R bottom. It's all the same damn thing because of how the numbers work out, right? So this is going to come out to be 130.189 times 10 to the 3 amp turns per Weber. And using this value, our current phi B times our equivalent reluctance divided by N, plugging our numbers in, we have 0.1 Webers times 130.189 times 10 to the 3 amp turns per Weber divided by 500 turns. Let's look at our units here. So we have Webers divided by Webers, so those guys cancel each other out. We have turns divided by turns, and all we're left with is something measured in amps, which is exactly what we want because we're trying to find current. And this comes out to be 26.038 amperes. So for that particular core geometry in material, we have to pass a current of 26.038 amps in order to sustain a flux of 0.1 Webers. Pretty appreciable amount of current. All right, so let's work another example here with a bit more complicated geometry. Process is going to be effectively the same. We're just going to have to think more about what our equivalent reluctance is going to look like. So let's say that my core structure looks something like this. Almost like a cinder block. And my coil is going to be wrapped around this central leg. And has N turns. Our dimensions of interest. So we're going to call this distance right here W1. It is 10 centimeters. This top path also has a width of 10 centimeters. This distance is going to be W2. And it is going to be 8 centimeters. And the middle and right leg also have widths of 8 centimeters. Our horizontal distance here, we'll call this L1. And that's going to be 80 centimeters. This distance here will be L2. 50 centimeters. That actually can't work out like that because 80 minus 10 minus 10 is definitely not 50. So let's change that to 60 and I'm going to have to look at the numbers. That total distance should be the 80 minus W1 minus another W1. Yeah. All right. And our thickness T is going to be 10 centimeters. And for this particular magnetic circuit, I'm only interested in finding my equivalent reluctance. So how am I going to transpose this physical structure into a magnetic circuit? What was that? Yeah, pretty close. So we're going to have, so let's look at something like this, right? So we're going to have the reluctance of our middle leg in series with our MMF, right? And then we're going to have, I'm going to draw this as just this right leg here, but we're going to break this down into smaller bits here in a second. So I'm just giving you a warning that I'm about to erase some of this stuff, right? So what Avery suggested is pretty spot on, right? So we have some left leg reluctance in parallel with some right leg reluctance, and then we have some middle reluctance there in the center. And we can break that left leg reluctance and right leg reluctance down into smaller parts because we have different physical shapes for these things, right? So we might want to call this guy up here R top left, this guy right here, R top right, this guy down here, R bottom left, this guy down here, R bottom right, like so. We can figure out what all of these pieces are pretty easy, right? So let's start with the left branch, which has an average flux path of however long that line is. So how long is that line I just drew in purple? The one that I drew in purple. Vertical line, okay? So L2 minus W1, okay? Looks like I forgot to provide you guys some information as well, so I apologize that we need to know mu to figure out REQ. So let's say that it's 5,000 mu naught, okay? All right. What's our cross-sectional area? W2 times our thickness, okay? And then we'll multiply by mu. So W2 was 8 centimeters, 10 centimeters, 5,000, 4 pi times 10 to the minus 9 henries per centimeter. L2 was 60 centimeters. W1, if I'm remembering correctly, was 10 centimeters. Yep. And putting all of this into our calculator, we wind up getting 7.958 times 10 to the 3 amp turns per line. So what about R mid and R right? So R right should be the same because this thing has symmetry. But what about the middle branch? So if I were to draw the length of the average flux path through this middle leg, it's literally the exact same length long, right? So it's still just going to be L2 minus W1 in length. And then what's the cross-sectional area of this branch? Well, it's going to be W2 times the thickness. So the middle branch is going to have the exact same reluctance as the left leg, as the right leg, right? So R mid will equal to R right will equal to R left. Okay, we got that part sorted out. So now let's look at that top bit here, right? So let's look particularly at that length right there. So this is going to be a little bit harder for us to figure out how to express in terms of our known quantities, right? So let's think about things really quickly here. I can do it in orange, okay? It is. No, not. Yeah, so this right here is 1/2 of L1, and then we also need to take off half of a W2. Right? So our top is going to be 1/2 of L1 minus W2. So I can just distribute that factor of 1/2. Right? Our cross-sectional area is going to be W1 times our thickness. So the cross-sectional area that I'm interested in is this cross-sectional area right here, which is W1 tall and T into the board. Then we have our mu. So just as a heads up, I noticed there's an error in my solution, so I'm going to have to actually recalculate this. So W1 was 10 centimeters. Yeah. Thickness also 10 centimeters. Mu 5,000 times 4 pi times 10 to the minus 9 henries per centimeter. Then up here we have a factor of 1/2, so I'm just going to put that at 0.5. And then we have L1, which was 80. And then W2, which was 0.8, if I'm not mistaken. Or excuse me, 8. And let's throw this into our calculation, right? So 0.5 times 80 minus 8. All of this is going to be divided by 10 squared times 5,000 times 4 pi times 10 to the minus 9. I get, let me write it down here. 5.730 times 10 to the 3 amp turns per weather. So that was the distance, or excuse me, the reluctance of what we called R top left. How is that going to compare to the reluctance of R top right? It's the same thing. What about the bottom left? Same thing. Bottom right, same thing, right? So R top left. So let's write that R top right is equal to R bottom left is equal to R bottom right, lowercase r, sorry, is equal to R top left. All right, so how do we find the equivalent reluctance of this whole thing? This is a little bit more difficult than our last example, because we've got those parallel branches and all that kind of stuff to take into account. So how do you find the resistance of a network, right? You take the voltage source out and look into the terminals where the voltage source was. So effectively, we're going to have something that looks like this. I'm not going to bother labeling any of these things because the labels are on the left-hand side. But this is our structure, right? So I would argue that our equivalent reluctance is going to be our middle branch plus, and then we have our two outside branches. They're in parallel and they're identical. So it's just going to look like half the reluctance of one of those branches, right? So 1/2 our top left plus our left plus our bottom left. Anybody have a question, comment, or concern about why the equivalent reluctance of the entire structure looks like that? Bailey, you looked confused, so I'm going to pick on you. You good? Okay. So substituting in our numbers, we're going to have 7.958 plus 0.5 times 7.958 plus twice 5.730. Our equivalent reluctance, good Lord, my penmanship is getting terrible, comes out to be 17.667 times 10 to the 3 amp turns per Weber. All right. So to this point, all of the structures that we've looked at have been completely solid. But sometimes we're going to have structures that have what are called air gaps that we need to pay attention to, right? So particularly structures that are used to model, let's say, rotating electric machinery and all that kind of stuff, where we have to have things that aren't physically connected in order to have rotation, something like that. We can also use this to look at relays and all that kind of good stuff. So this next part is going to be called air gaps in magnetic circuits. So I'm going to draw a core structure here. And I'm going to draw it such that the air gap is very exaggeratedly large. So this is our core structure. Let's say that our coil is wrapped around this left leg of this thing. N times for what it's worth, and that our current is flowing in this direction. Right? So for this particular structure, we can see that there is a break in our core that we call an air gap. what do you guys think the permeability of an air gap is going to look like? So remember that when we're dealing with our ferromagnetic cores, right, we have a permeability that's extraordinarily large compared to the permeability of free space, right? Thousands, if not tens of thousands of times that of free space. What do you think the permeability of air is? Damn near exactly the permeability of free space. So in our air gap, we are going to see that mu is equal to mu naught. Our air gap has some amount of length, so we're going to call this L subscript G. So this is our gap length. And just to be super clear here, everywhere that's blue is our magnetic core. And I'm going to call this permeability mu C. That's literally just the core permeability. We'll give it numbers when we deal with materials and all of that kind of good stuff. So if our air gap length LG is small, and we consider small to be smaller than the dimensions of the core faces, the magnetic flux will follow the path defined by the core, and the air gap can simply be treated as a reluctance that's in series, but it's going to have its own reluctance properties because it's a different material, right? So because the permeability of the air gap is much less than that of the core, the magnetic flux is actually going to leak out of the sides of the air gap as fringing fields. So I'm going to attempt to draw something here. So this is the portion of our core near the air gap, right? So we just have something that looks like this. We have our air gap in the center. And these fancy squiggly lines are me just saying we're cutting the rest of the core out because we don't care about it, right? So what we're expecting to have happen is that our field lines are going to spread out, right? So right here through the center, we're going to have just a straight path for our flux. But as we get a little bit away from the center, we're going to see that our lines are effectively bent a little bit. Something like this. And it's spreading out because of the change in permeability that's seen. So, since the flux spreads out in this region, it actually sees a larger cross-sectional area than the flux that's traveling through the core sees. Okay? So we are going to define the gap cross-sectional area, AG, to be the thickness of our core plus the gap length times the width of our core plus the gap length. So just for the sake of argument here, let me define the thickness on our original diagram. So there's the thickness, and then there's the width. So our general rule of thumb is to just increase the core dimensions by the gap length in both directions and use that to calculate our new area that the flux passing through the air gap sees. So let's put this into practice. by doing one last example problem for today, and then I'll leave you guys to do some work. Right? So this structure right here is effectively an electromechanical relay. We have a horseshoe-shaped core. Like so. And then over here, out to the right, we're going to have the separate piece, and not that it particularly matters to us, but it might be on a string, so that effectively magnetic attraction is going to try to move this vertical piece here to the right, closing those contacts. Okay. And we cause that actuation by the presence of an electromagnetic coil over here on the left, carrying some current I and having N turns. So let me define some dimensions for you guys. So this is our width W, this is also W, this is also W, this is also W, and W is 1 centimeter. It's going to be a big relay. This length will be L1. Let's call that 8 centimeters. This length here will be L2. Call it 4 centimeters. Our thickness, T, will be 1 centimeter. And then lastly, the length, that looks like a Q, not a G. Our gap length, LG, will be half of a millimeter. Remember that our air gap needs to be small compared to the cross-sectional area or the dimensions of our core in the region of the gap in order for us to be able to actually sustain magnetic flux crossing that air gap. Okay. So I want us to find the magnetomotive force necessary to maintain a flux of phi b is equal to 100 microwebers in the core if our core permeability is 1000 mu naught. So what's my magnetic circuit going to look like? Series path of reluctances, right? Because our flux just sees this path, right? This is the path representing the distance that our flux travels. So our magnetic circuit will look something like this. Here we have our left branch Here we have our MMF. Then we have the reluctance of our top branch in series with the reluctance of our gap. Here's the reluctance of our right branch. Then down here we have our bottom. And then we have our bottom branch is in series with another gap reluctance. And because our gaps are the same size, they're going to be equal. The reluctance of the top path is going to be equal to the reluctance of the bottom. The reluctance of the left path is going to be equal to the reluctance of the right. So we really only need to calculate three things. Okay. So let's start with the leftmost path. So what's the distance my flux travels? L2 minus W, right? What's my cross-sectional area? W times 2. Absolutely right. And then because we have two different materials, I'm going to make a point to call this mu C here. Okay. So plugging in numbers, L2 is 4 centimeters minus 1 centimeter. Down here, we're going to have 1 centimeter times 1 centimeter times 1,000, thank you, times 4 pi times 10 to the minus 9 henries per centimeter. And I got 2.387 times 10 to the 5 amp turns per Weber. The right path has the exact same reluctance. All right. So what about our top? What's the total length that our flux travels as it goes across that top section? So to be clear here, what we are considering would be from here to here. But then also that little bit right there. So we are intentionally not including our gap distance in here because we don't want to add extra reluctance to our core material because the gap has different material properties or whatever. So let's look at things here really quickly. I believe you're right. So yeah, so we already have this distance of W. So this guy right here is going to look like half a W. And then this distance right here is L1 minus half a W. So L1 minus half a W plus half a W is just L1. Our cross-sectional area is still just going to be W times T. And because we're still in the core, we're going to use mu C. So that's going to look like 8 centimeters divided by the exact same denominator we had previously. 1 centimeter times 1 centimeter times 1,000 times 4 pi times 10 to the minus 9 henries per centimeter. And I got 5.570 times 10 to the 5 amp turns per Weber. Our bottom is the exact same thing as our top. And then lastly, we have our gap. So what's the distance our flux travels as it passes through the gap? The length of the gap, right? So just L sub G. Keep writing Q's. What's our cross-sectional area going to be? The width plus LG times the thickness plus LG, because whenever we're in the region of the air gap, we increase the core dimensions by the gap length to account for the fact that the flux is allowed to spread out in that region. So this is going to be W plus LG times T plus LG. And then we have our permeability. What's the permeability of the gap? Mu naught. So this is going to look like, so 1 centimeter plus half a millimeter is going to look like 1.05 centimeters. Then 1 centimeter plus half a millimeter is going to look like another 1.05 centimeters. Then I have mu naught, which is 4 pi times 10 to the minus 9 henries per centimeter. And then up here, I have 0.05 centimeters. I've chosen to express everything in terms of centimeters so that we've been consistent with what we've been doing so that our units will work out the exact same way as they have been. And so what I find here is that I get 3.609 times 10 to the 6 amp turns per Weber. Fantastic question. That is something that I was actually going to point out here in a moment, but that's a great question. Okay. So, Caitlin, right? Yeah. So Caitlin asked, why is the reluctance of the gap larger? Right? It's pretty significantly larger. Right, so in our previous things, we had things times 10 to the 5, 10 to the 5. Now we have something times 10 to the 6. When we add everything up together, we are going to find that the total reluctance of the air gap actually makes up 82% of the reluctance seen by our flux here. So why is it so much more? Well, remember that our core is concentrating our flux, right? And the air gap is letting it spread out. So it sees a harder path, I guess, to travel. Mathematically, the fact that we are not dividing by 1,000 here is going to make our numerator significantly larger, right? So we usually have some large number down here in the denominator that's making the whole thing small, but because we don't have that large scaling factor here, our relative permeability, that's making the overall reluctance very, very large. So if we are trying to provide the most efficient flux path as possible, we need to figure out how to minimize our air gaps as much as possible in order to have a nice, efficient electric machine. So Our equivalent reluctance will just be our left plus our top plus our gap plus our right plus our gap plus our bottom, and adding all of these guys together, I got 8.809 times 10 to the 6 amp turns per Weber. And as I mentioned a moment ago, twice our gap is approximately equal to 82% of our equivalent reluctance. So just to circle back around to things, we were asked to find MMF. We found our equivalent reluctance. What do we need to do now? So going way back to the beginning of the lecture, our magnetomotive force, MMF, is equal to flux times equivalent reluctance. We were given a flux of 100 microwebers. We found our equivalent reluctance to be 8.809 times 10 to the 6 amp turns per Weber. And so our MMF is 880.946 amp turns. All right, let me put the conversion factor in there. So we have, let's see, 10 to the 6 microwebers divided by, excuse me, 10 to the 6 microwebers per Webers. So if we look at things here, microwebers cancels microwebers, Webers cancels Webers, we're being left with amp turns. We have 10 to the 6 divided by 10 to the 6, so those guys cancel out. So we have 8.809 times 100 is 880.9. All right, we have 20 minutes left. So do as much of this as you can. Understanding it's probably not going to be all of it. I'll be lucky if it's one of the 2 problems. That's okay. Again, the in-class assignment is not graded for completeness or correctness. I just want you guys working on things. By the way, you may have noticed on Canvas that your first homework assignment has been posted. It is due 1 week from today at midnight. The in-class assignment 1 that we worked together is due, I think I have it set due to be midnight tomorrow. Literally just take a picture of it and upload it. And then in-class assignment number 2, which I want to be really clear here, is not graded for completeness or correctness. So whatever you get done until the end of class is perfectly acceptable to turn in, is due before our next class meeting. So it's due on Thursday at noon. And that'll be the modality that we go with going forward. You're welcome to take extra time if you want to finish the in-class assignment, but it is not required of you. Thank you. If you have any questions, please feel free to ask.